Hello. In today's video we're going to be looking at chapter 14. We're going to be looking at our lecture 8 and we're going to be looking at the first 3 learning objectives. We're going to be using our integrated rate law. So we're going to be finding out what our integrated rate law is, using it to determine the concentration of a reactant at any given time without a reaction for either a 0th order, 1st order, or 2nd order process. We will then apply the relationship between the rate constant and its half-life, so we can either use the rate constant to determine its half-life or use the half-life to determine its rate constant. Again, this will be based on whether it's a 1st order, 2nd order, or 0th order reaction. And then we are going to use a table of reactant concentrations as a function of time to be able to determine the order of a reaction. So with these 3 learning objectives, we're really basing everything on the integrated rate law, and we're going to compare it to the 2 rate equations we've looked at so far, our general rate law and our relative rate law. So our relative rate law is what we looked at first. So our relative rate law, it is used to calculate a molecule's relative concentration change over time, and we can use that to base our rate on it. So remember, that is if we're talking about A going to B, it was negative delta A delta T equal to our rate. So this is used to calculate a molecule's relative concentration change over time. And this could be reactant or product. Okay. Now, a note about our relative rate equations. We cannot use them in order to calculate an actual concentration, just proportional concentrations of reactants relative to products, or vice versa. Okay. Our general rate law, the next thing we looked at, we also called our differential rate law. This is where we have rate equal to K, our rate constant, A to the M, B to the N. If we're talking about A plus B goes to C plus D. Okay. In this, we are looking at how our rate can be affected by a reactant's concentration. So looking at how the rate changes by altering a reactant's concentration. Okay. With this, we can't calculate a molecule's concentration change over time. So our relative, we can look at relative changes. Our general, we can look at how rate is affected by changes in concentration. But what we're going to look at today is what's called an integrated rate law, which combines the two to form an equation that we can actually use to calculate actual concentrations of reactants and products over time. So our integrated rate law is used to calculate actual concentrations of reactants and products over time. And like I said, we get the integrated rate law by combining elements from both the relative and general law equations. Okay. Now, as a note, each one of our integrated rate laws are going to be based on the overall reaction order. So there'll be different forms based on whether it's first order, second order, or zeroth order. Okay. And with each of these, we're only going to look up to the second order, but of course, if there's a third order, we would have a different integrated rate law based on that. But they get pretty messy if we get beyond second order. In addition, we're only going to be looking at integrated rate laws where we're looking at zeroth, first, or second order processes where we only have one reactant, or what we're going to also look at is a pseudo first order process, where we're first order in one substance, but we have a second order process. So they get kind of complicated, but we're only going to go over kind of the forms and how to use them. Okay, so with our first order, remember that a first order reaction, its rate depends only on the concentration of a single reactant. As we double its concentration, we double our rate. Okay, so what we're going to do in order to calculate first order integrated rate laws is once we have our integrated rate law, our rate constant, and our initial concentration, we can determine our concentration of A at a point T. So the integrated rate law uses, let's try this out real quick, uses the initial concentration, so our A naught, rate constant, K, and time, T, to determine AT, which is the concentration of A at time t. Okay, so you have to have your rate constant. You have to have your initial concentration. You have to know what point in time you're looking at. Okay, so let's see how we actually developed this equation. So the way that this is taken is you have your your relative rate equation and your general rate equation combined. So here's our relative, and then our general for a first order process. So we take our relative rate equation for a first order process, our general rate equation for our first order process, we combine them, setting the rates equal to each other. We get negative delta A over T is equal to KA. And then this is then integrated. And what we get is ln A at time t minus ln A naught is equal to negative KT. Okay. So I do have a little bit more math on the typed PowerPoint if you wanted to look at it, but it's not really important to understand how to use a integrated rate law. So I just wanted you guys to know that it is based on both the general and relative, and just some integration allows us to get to our integrated rate law for a first order process. And with this, our AT is our concentration at point or at time t. A naught is our initial concentration. K is our rate constant, and then T is our time t. So it's basically just plug and chug. So let's try it out with the following learning objective. So we want to know what the concentration of hydrogen peroxide is at 1250 seconds using the following information and this graph right here. So here we have our K value, we have our time, and if we look at this graph, we see that we have our initial concentration, right? So our A naught is equal to 1.00 molar. Our time is equal to 1250 seconds. And our K is equal to 1.06 times 10 to the negative 3 molarity per minute. Now, hopefully you notice that our T and our K are not in the same units, so we need to convert one or the other. I'm going to go ahead and take my time and put it into minutes, which is 20.83 minutes, so that when we multiply our time by time value by our K value, we cancel out those minutes and get molarity. Okay, so now all we need to do is plug into our equation. So we've got ln H2 O2 at time t, which is 2083, minus ln H2 O2 naught, so our initial concentration of that, is equal to negative KT. So we have ln H2 O2 minus ln 1 equals negative 1.06 times 10 to the negative 3 times by 2083. And I'm just keeping units out because it just makes it more complicated than it needs to be. So when we solve for the right side of our equation, we're going to get ln H2O2 2083 is equal to negative 0.02208. As a note, ln of 1 gives us 0, so I just kind of canceled that out. And then when we take both sides to the e to get rid of our ln, or our natural log, we get H2O2 concentration equal to 0.978 molar. Now, hopefully this makes sense. If we look at this elapsed time down here, it's in minutes. So 20 minutes is somewhere, I don't know, right over here. Which means we're like right here. Which makes sense that we haven't changed much concentration. Okay? Okay. Now, next thing we want to do is look at what happens as we rearrange our first order process. So if we look at ln AT minus ln A naught, so our integrated rate law, if we rearrange this, we can get something that looks like this. Okay, and hopefully what you guys see here is a y equals mx plus b. Okay, so this is how we would actually graph our integrated rate law. So if we have our y equal to ln AT, our x equal to t, I don't know what I'm doing over there, then we have, and we graph these, so time versus ln A, we would have a k, which is our slope, or rather a negative k for our slope, and then ln A naught will be equal to our y-intercept. So, one of the things I want you to take away from this, beyond just, yes, if you graph ln A versus time, you can figure out your k value, right? So that's one of the most important things, graphing ln A versus time, or ln A of several different time points. You can get your rate constant. Another thing that I want you to note is that if you do ln AT versus t, and you have a linear plot, then you have a first order process. So only first order processes will have a linear relationship between ln A versus time. Okay? So, next thing we want to look at is the half-life for a first order process. So a first order process, our half-life is the time it takes to consume half of our initial concentration. We put it as T1 half. Okay. So, again, on the PowerPoint, I show all the math to get that, where you take your integrated rate law, and you take your T as T1 half, and you solve for T1 half. Once you solve for T1 half, you get a value, or you get a equation, T1 half is equal to 0.693 over K. So this is the half-life equation for a first-order process. Again, if you want to look at the math, it's on the PowerPoint for you guys. But the important thing to note is what our actual half-life equation is for a first-order process. Okay, so let's try and use this equation in the following question. So decomposition of N2O5 is a first order process. If we know what its half-life is, we want to determine what its rate constant is. So our T1 half is equal to 0.693 over K. So this is a simple plugging in our T1 half and solving for K. Okay, so our T1 half is 4.03 times 10 to the 4 seconds. That is equal to 0.693 over K. We solve for K, we get a value of 1.72 times 10 to the negative 5. And this is a first order process, so our rate constant is s to the minus 1. Okay, so again, simple plug and chug to determine what our K value is for a first order process. Okay, I'm going to go a little quicker through the rest of this because it's just looking at the equations for second order and then zeroth order. So if we have a second order reaction, we have a reaction whose rate depends on the concentration of one reactant squared or two reactants, which we will not look at. So when I say the squared concentration, what I mean is that as we double our concentration, we're going to quadruple our rate. And if we are second order because of two reactants, that means we're first order in each of the two reactants. Giving us an overall second order process. So those are two ways that we can have a second order process. We will not look at this one. So, not looking at. Directly. We will look at what's called a pseudo first order, but the math to get a second order process is very, very messy if we have two different reactants. So we're going to stick with second order with one reactant. And with this, our integrated rate law for a second order process again, math on PowerPoint if you want to look at it, but it's negative 1 A at time t plus 1 over A naught is equal to negative KT. Okay, so this is our integrated rate law for a second order process. Let's use it in a problem. Let's say we have this process right here. We've got 2H2, 2HI, sorry, breaking down into H2 and I2 We have a K value here, and let's say we want to know at T equals, I don't know, 1250 minutes. So instead of seconds this time, let's look at minutes. So here we have -1 over hi at time t plus 1 over hi at time 0 is equal to -kt. We're going to place our k value in here. Our k value is in molarity per minute. Our time is in minutes, so we don't need to do any changes in that. So we get -1 over hi at time t. Again, our initial concentration is 1 molar. And we're just going to place in our k value and our t value. And let's solve for our concentration at time t. Okay, so we get 1 over hi at time t is equal to 646.5. They were both negative, I canceled out the negatives, and then we can solve for hi at time t, and that is equal to 1.55 times 10 to the -3 molar. If we look, we're at 1250, that's somewhere right around here. That seems like a reasonable value. It's going to be pretty low, right? So, I like it. There we go. Okay. We can, of course, rearrange our second order integrated rate law. When we do that, we can get the following form. 1 over AT is equal to KT plus 1 over A naught, where this is our Y, M, X, and B. So if we do 1 over AT versus time, we get a linear relationship. So for a second order process, 1 over A versus time is linear. And with that, we get a slope that is equal to a positive K. So not a negative like we saw with the first order process. We have a positive K as our slope. And our y-intercept will be equal to 1 over our initial concentration. Okay, so just by graphing this, we can get a lot of information out of our integrated rate law. Okay, so again, the takeaway here is we can solve for our rate constant using our slope, and that if we have 1 over A versus time, that is a linear relationship only if we have a second order process. Okay, we can then look at our half-life here. So our half-life, we can do the same math, and again, that math is on the PowerPoint, but our half-life equation here, T1/2 for a second order process is equal to 1 over K times by our initial concentration. So if we have initial concentration, our initial concentration is taken into account for a second order reaction. It is not for first order, right? So again, with our half-life, we can relate the amount of time it takes to deplete half of our initial concentration to what our rate constant is, which should make sense, right? If we have a rate constant telling us how fast a reaction is, we should be able to use that information to determine how long a half-life is. Okay? Okay. So let's use that T1 half. Or let's actually use the half-life equation along with our integrated rate law to answer the following question. So the dimerization of C2F4 to C48F8, so 2C2F4 goes to C4F8. This is second order with respects to C2F4. If we want to know what our C2F4 concentration is after 205 seconds, using our initial concentration and our rate constant. So let's use that information to solve for that. And let's solve for our T1 half as well. Okay, so we've got A naught equal to 0.100 molar. Our time is 205 seconds. Our K is equal to 0.0448. Seconds is minus 1, molarity is minus 1, which should make sense because it's a second order process, and that is a unit of K for a second order process. We are looking for a change in concentration, so we're talking about our integrated rate law. 1 over A, 1 over AT is equal to KT plus 1 over A naught. In this case, it's 1 over C2F4 at, let's do, keep consistent, at 205 seconds is equal to our K value, 0.0448 times by our time, 205 seconds, plus 1 over our initial concentration, 0.100 molar. Calculate this out. We get 1 over C2F4 is equal to 19.2. And then we can solve for our C2F4 concentration after 205 seconds. That is 0.0521 molar. We can also, as I said, take this and solve for our T1 half using T1 half is equal to 1 over K C2F4 naught. So T1 half is equal to 1 over 0.0448 molarity -1, seconds -1, times by our initial concentration of 0.100 molar. We get a T1 half equal to 223 seconds. Okay. Fantastic. Let's move on to a zero order process. Zero order process, the rate depends on no reactant. The rate does not depend on reactant concentration. Okay, so here we get A T minus A naught is equal to negative KT. PowerPoint maths. So this is zero order. Integrated rate law. let's try out an equation with it, or try out a problem with it. So here we have NH3 going to N2 and H2. Our K value is 1.5 times 10 to the negative 3 molarity per, or molarity times seconds, or molarity per seconds rather. And I don't know, let's look at time 700 seconds. So we use our first order process. A t minus a naught is equal to negative 1.5 times 10 to the negative 3 times by t. So our NH3 concentration at 700 seconds minus our initial concentration, 2.00 molar, is equal to negative 1.5 times 10 to the negative 3 times by our 700 seconds. And we get a NH3 concentration at 700 seconds equal to 0.95 molar. And if we look at 700 seconds, that is about where it's at. Fantastic. So very easy to use. And of course we can rearrange this. If we rearrange to get AT is equal to negative KT plus A naught, we get a linear relationship between AT versus time. So here we're looking at just concentration versus time. When we take concentration versus time, we get a slope equal to negative K, and we get a y-intercept equal to A naught. So again, we can very easily determine what our A naught is by using our y-intercept. We can determine what our slope is, or our y is, our rate constant, using our slope. And keep in mind that if we have our concentration versus our time, unmodified concentration versus time, we get a linear relationship only if we have a 0th order process. Our half-life here is T1/2 is equal to A naught over 2 times by K. Okay, so again, the math is on the slide, but this is our half-life equation for a 0th order process. Okay, let's real quick summarize our laws. So our rate law, we're talking about our relative. Differential, that's our general. Integrated is what we looked at today. We want to look at what makes a linear plot for each one of these, what our unit of K is, and our half-life. So something like this you should be able to fill out. Okay, so with our relative rate law, we have rate is equal to, oh, sorry, this is general rate law. Rate is equal to Ka for a first order process. With a second order process, rate is equal to Ka squared, and 0th rate is equal to just K. It doesn't depend on any of our reactants. We can take our general rate law and our relative rate law and combine them. This is supposed to be combination. And we get delta A delta T equals Ka for a first order process. Delta A delta T is equal to Ka squared for a second order process. Rate is equal to delta A delta T equals K for a 0th order process. Okay. And then we can take and integrate these to get our integrated rate law of ln AT is equal to negative KT plus ln A naught for our second order process. 1 over AT equals KT plus 1 over A naught. And then for a 0th, AT equals negative KT plus A naught. And these are also our y equals mx plus b. So from here, we can get our linear plot by taking ln AT versus time for a first order process. 1 over AT versus time for a second order process, and AT versus time for a 0th order process. Our units of K, S is minus 1 for a first order process, molarity is minus 1, seconds is minus 1 for a second order, and then molarity divided by seconds for a 0th order. And then lastly, half-life, T1 half is equal to 0.693 over K for a first order process, 1 over K A naught for a second order process, and then A naught over 2K for a 0th order process. Okay, so let's just look at this next part real quick. So we've got the decomposition of N2O5, and when that decomposes, we get the following data. So we want to use this data to determine what our rate law is, what our K is, and what our half-life is, and A naught. Okay, so hopefully you guys have gotten at this point that you can look at the linear plots to determine what your overall reaction order is. Okay, so if we look at our time versus A, so just A versus time, we see that we get a nonlinear plot. Here, our ln A versus time is linear. And then the last one, 1 over A versus time, is not linear. Now if we go back here, we look and see what produces a linear plot for each one. If we have a first order process, it'll be ln A versus T. Second order is 1 over A versus T. 0th order is A versus T. A versus T is not linear, so it's not 0th. 1 over A versus T is not linear, so it's not second. But if we have ln A versus T, then we have a first order. Okay, so from this, we can then use this equation, which is our y equals mx plus b, to determine what our different values are. So our K, in the case of a first order process, is equal to negative, or slope is equal to negative K. So our slope here is equal to negative 6.26 times 10 to the negative 4, which means that our k is equal to 6.26 times 10 to the negative 4. So it's the positive value of that. Next, we want to determine our rate law, which we already did. So our rate law, we have first order. So our rate is equal to k and 205. Our A naught is going to be our y-intercept will be equal to ln A naught. So this right here, ln A naught, is equal to our y-intercept of 8.46 times 10 to the negative 1. So if we take the e of that value, we get an A naught equal to 2.33 molar. Okay. And then our half-life for this T1/2 is equal to 0.693 divided by k. Our k value here is 6.626 times 10 to the negative 4. So we get a T1/2 equal to 1,046 seconds. Okay, the last thing I want you guys to look, or we want to look at, is our second order process, where we have first order in 2 reactants. Okay, so here, if we have second order by having first order in 2 reactants, the math is very, very crazy. So instead, we do what's called pseudo first order kinetics. Which means we take one substance and we make its reaction concentration so high that it effectively doesn't change during the reaction. So you look at the other substances. So what you get is rate is equal to k naught A. So you get, or k, little funky k, where your funky k is equal to kb. Okay, so you're looking at just a change of A versus time, and you will get a linear plot for that by taking your B concentration and making it very, very large so it's not changing. And then what you do is you solve for this. And then once you solve for that, you can take this k value here and solve for your actual k value. Okay, we will not be doing that in class. I just wanted to bring it up because you guys will see it in lab. It will actually be the lab we'll be doing next. And yeah, I just wanted to note that. Okay, that is everything. Sorry this one was so long. The next one will be super short. Okay.